So welcome to the first of three videos on transition metals. And this video, this first lesson, will look at transition metals and their electron arrangement, and we'll also look at how transition metals can have various oxidation states and how we can describe that in terms of an oxidation number, an oxidation state, and look at the oxidation and reduction of transition metals. So transition metals are what we would typically call the D block metals, and they form ions with incomplete or partially filled d orbitals. So actually within the block of within the D block, not everything is technically a transition metal. Some of them, for example, zinc, cadmium, mercury, have completely filled d orbitals, which would technically exclude them from being a transition metal. However, they often get described, the whole block, as being transition metals. So they're the orange part in that picture. Now, when it comes to filling electrons into the d orbitals within transition metals, we actually have to look at not only the d orbital, but the s orbital. In advanced higher, you're only really asked to work with the first row transition metals. And so if we were using spectroscopic notation, using the noble gas notation for that, everything would be argon, and then you would be looking at filling the 4s and the 3d orbitals. And you can see the rules for filling d orbitals come into play. So you can see the Aufbau principle, you can see Hund's rule, and you can see the Pauli exclusion principle coming into effect. Now remember, the transition metals, the D block comes right after the S block, and so always you tend to have the 4s orbital filled. But there are two exceptions, which we have already covered, but we'll go over again here. So we'll start with scandium. Now scandium is the first transition metal, and it has 2 electrons filling the 4s orbital, and then what we have is 1 d electron in one of the d orbitals. Titanium and vanadium follow the exact same pattern, and what you can see is Hund's rule coming into effect because the 3d orbitals are degenerate, they have the same amount of energy, and they get filled singly or individually before we see any pairing up. Now chromium is where we see an exception to this rule. And in chromium, what we actually get is 1 electron in the 4s orbital and 5 electrons filling each of the 3d orbitals. The reason for this is because the 4s and the 3d orbitals are quite similar in energy. And having the 5 3d orbitals all filled individually is energetically more favorable than having a completely filled 4s orbital and 4 electrons in the 3d orbitals. So because there's that very close energy difference, rather than complete the 4s orbital, what happens with chromium is that we end up with 1 electron in the 4s orbital and then 5 electrons in the 3d orbitals. You might ask yourself, well, why does that not happen for vanadium? Why doesn't vanadium fill 1 electron in each of the 3d orbitals and have nothing in the 4s orbital? That's because it's just the difference in having nothing in the 4s orbital compared to having 1 in the 4s orbital. It's much less stable to have nothing in the 4s orbital than 1 electron in the 4s orbital. So that's why it doesn't happen with vanadium. And then manganese goes back to our normal system, 2 electrons in the 4s orbital and 5 electrons, 1 in each of the 3d orbitals. What we see happening for the second half of the first row of the transition metals is we just start to see pairing up of electrons. So in iron, we have 2 electrons in the 4s orbital, and then we start to pair up. So the first of the 3d orbitals gets paired, the rest are single. Nickel and cobalt follow this pattern exactly, completely filled 4s orbital, and then just starting to pair up. Copper is where it gets to be an exception again. In this case, one of the electrons from the 4s orbital moves into the 3d orbital, so that we end up with a completed 3d orbital. And again, that's because having a completely filled 3d orbital is actually more energetically stable, more energetically favorable than having an incomplete set of 3d orbitals, but a complete 4s orbital. A full set of 3d orbitals is more stable than not, essentially. And zinc, what we have is everything paired up. So the pattern follows the normal rules, however, you do need to know the exceptions when it comes to chromium and copper. Now, transition metal ions, they form, what makes transition metals unique is that they can form ions of different charges. Now we have to know they are metals, and metals form positive ions, so this is achieved by losing electrons. And we would describe that as oxidation. Oxidation is loss. So because transition metals can form different ions by losing different numbers of electrons, we would describe them as having different oxidation states. And an important thing to note is that whenever transition metals become ions, they always lose the 4s electrons first before the 3d electrons. And you will notice that every transition metal, every first row transition metal, is able to form a 2+ ion. When it forms a 2+ ion, what happens in the case of most of them is that they're losing 2 electrons from the 4s orbital. In the case of copper and chromium, they're losing 1 electron from the 4s orbital, and then they are losing an electron from the d orbital. But always they lose 4s electrons first. Now, as I said before, the 4s and the 3d orbitals are very close in energy. And because whenever transition metals form ions, they lose their electrons from the 4s orbitals, this would give us an indication that actually, in terms of energy, the 4s orbital is higher in energy than the 3d orbital, because whenever you lose electrons from higher energy orbitals first. And if the 4s orbital is higher in energy than the 3d orbital, if we consider the Aufbau principle, which says we should fill orbitals in order of increasing energy, technically we'd be more correct in putting the 3d before the 4s. However, there is still a lack of understanding as to whether or not that is the case, because as we see whenever the electrons get filled, most transition metals will have a completely filled 4s orbital before they fill the d orbitals. And so this is something that's not fully understood, and so you'll often see the 4s and the 3d orbitals written in different orders. Sometimes you will see it with the 4s orbital written before the 3d orbital. Sometimes you'll see the 3d orbital written before the 4s orbital. Do not worry, or do not think that, oh, your understanding is completely shaken if you see it written the way that you are not used to, because it is really dependent on the chemist and their interpretation, how they choose to do it. Conventionally, in most textbooks, they put the 4s before the 3d, but it's just in case you're ever looking at something on the internet and you see the d orbital put before the s orbital. And that's just why. It's because there's very close in energy and it's not completely been decided which one should go first. Now, we were talking about transition metals forming ions, and this is where we get into our understanding of the term oxidation state and oxidation number. So whenever an atom forms an ion, it's described as having an oxidation state or an oxidation number. And there are rules for determining oxidation number. So the first rule is that if you are an element on your own, you have an oxidation number of 0. So all the transition metals, if they exist just as the pure metal, so for example, if you had iron on its own, or if you had titanium on its own, it would have an oxidation number of 0. If you are an ion made just of one element and you have a charge, so for example, if you were an Na plus, a sodium plus ion, your oxidation number is equal to your charge. So a sodium plus ion would have a charge of +1, an oxidation number, sorry, of +1. If you are a magnesium ion and you're a magnesium 2 plus ion, your oxidation number is +2. It also works for negative charged things as well. So an oxygen atom has a charge as an oxide ion of 2-, and its oxidation number would be -2. So be aware whenever we're describing oxidation number, we put the sign before the number, but when we're describing charge, we put the number before the sign. So there we just have examples. An Fe2 plus ion has an oxidation number of 2 or +2, and the sulfide ion S2- has an oxidation number of -2. Whenever we have a molecule or we have an ion that's made of multiple atoms, the sum of all the oxidation numbers of each atom add up to the total charge of the compound or ion. So for example, a water molecule is overall neutral. The oxygen is described as having an oxide, which is 2-, and each of the hydrogens having a +1. So 2 times +1 with then a -2 equals 0. So that always comes to being the case. And there are certain atoms or ions that always have fixed oxidation numbers. Transition metals are not like that. And so whenever you're wanting to work out the oxidation number of a transition metal, you need to look at the elements around it and use those to help you find out what the oxidation state of a transition metal is. So here are some elements that always form ions of exact oxidation state. And even if they're not ions, even if they're part of molecules, we would describe them as having these oxidation numbers themselves. So oxygen always has an oxidation number of -2. Hydrogen, there are some very rare cases where hydrogen actually has an oxidation number of -1, but most cases, hydrogen you can consider it as having a +1 oxidation state. All halogens, so chloride, fluoride, bromide, iodide, etc., they have oxidation numbers of -1, and alkali metals, so your sodium, lithium, etc., have an oxidation number of +1. What's not written on the slide are the group 2, the alkali earth metals. They will always have an oxidation number of +2. And you will have to use those constant oxidation states to help work out the oxidation state of some transition metals. I've got a couple of examples here. I've got titanium dioxide, which is a neutral compound, and then I've got the permanganate ion, which obviously is an ion. So the first thing you need to look at in each case is the charge. So we'll go through titanium dioxide first. Titanium dioxide has a neutral charge, which means the sum of all the oxidation numbers must equal 0. We just can break it down into a sort of algebra. We've got 1 titanium, we've got 2 oxygen, and together they must equal 0. Oxygen always has an oxidation number of -2, so we know that titanium plus 2 times -2 equals 0. Titanium minus 4 equals 0, which means titanium is plus 4. In permanganate, the charge is minus 1, so we know that the sum of all the atoms, the sum of the oxidation numbers of all the atoms must add up to minus 1. So we have 1 manganese and 4 oxygens. We know that oxygen is always a minus 2. So manganese minus 8 equals minus 1, and so manganese ends up with a plus 7 oxidation state. So what we've got here are a set of examples for you to try. So in each case, work out the oxidation state of sulfur. So sulfide is just sulfur on its own. The other 4, B, C, D, and E, are all found in the data booklet on the on the table at the top of page 21. So what I'd like you to do now is pause this video and have a go at working out the oxidation state of sulfur in each of these examples. And then whenever you resume the video, I'll start the answers. Okay, so I'm hoping you've had a go there for yourself. Here are the answers. So sulfide, it's S2 minus because it's a group 6 element. And because there's only one atom in there, the oxidation number is equal to the charge, so it's minus 2. Sulfite, the formula is SO3 2 minus, and that means that sulfur must have an oxidation number of plus 4. Sulfate, SO4 2 minus, well, you can see the only difference is an extra oxygen. And in order to balance that out, sulfur needs an oxidation state of plus 6. Hydrogen sulfide, which is HSO3 minus. In this case, what we have got is sulfur with an oxidation state of plus 4. And thiosulfate, S2O3 2 minus, has sulfur with an oxidation state of plus 2. So you can see that it's not only transition metals that can have lots of different oxidation states, and that's something to be cautious of. So I'm hoping that you were able to get all of those. So transition metal compounds form colored compounds, and the reason why they form colored compounds we'll get into in more detail later on. But the color changes in compounds depending on the oxidation state. So copper in some of these compounds at the top, they're all sort of shades of blue or green, that's common for copper. But in some of these, copper may be 2+ and some of them 1+. With the cobalt compounds, some of them are pink, some of them are blue or green. Again, that's usually in cobalt compounds, depending on whether the cobalt is a 2+ or a 3+ charged compound. The transition metal compounds, they change color as they change oxidation state. Some of the colors are very, very, very distinct. So manganese at the bottom left of the colored ones, manganese 2+ is a really, really pale pink. Often if you see the manganese 2+ solution, you'd say it's colorless. That's how pale it is. Whereas the 7+ one, that's what permanganate looks like, and that's the really bright purple intense color that you have seen before. Moving to the next one along, iron. Iron also switches quite easily between iron 2+, which is green, and then to bright orangey yellow color for iron 3+. If we look at the top, vanadium and chromium are the ones that probably have the biggest range of colors. You can see for vanadium, as we go from 2+ to 3+, we go from purple to green. And then we go again from 3+ to 4+, we go to blue, and then we go to yellow. And with chromium, we can go from blue to green to orange. And some of these ones at the bottom, cobalt, nickel, and copper. Cobalt 3+ is a more green color in solution. Nickel tends to always be green. It doesn't form a lot of different oxidation states actually. And copper, usually in solution, is a 2+ ion and it looks very blue. However, as we saw in the previous slide, whenever it solidifies or crystallizes, it can form lots of different colors. Now, whenever we're talking about transition metals, at changing oxidation state, what we're looking at and what we're talking about are redox reactions. Now, whenever we talk about oxidation in relation to transition metals, what we're looking for is an increase in oxidation number. So previously, you've encountered lots of different definitions of oxidation. So you would have had oxidation as loss of electrons. You would have seen oxidation is addition of oxygen, and oxidation is removal of hydrogen. Well, now we've got another definition of oxidation, and that is an increase in oxidation number. And if oxidation is an increase in oxidation number, reduction is a decrease in oxidation number. And so you can use the oxidation number to work out which process has happened to a chemical. Usually these questions focus on one particular atom within a compound rather than the compound as a whole, and it's typically a transition metal. So for example, here it's obviously not a balanced equation, but we can see that iron 3+ going to iron trichloride going to iron dichloride, the oxidation number has gone from 3 to 2, which represents a reduction. Here we've got copper oxide, that would be copper 1 oxide, going to copper sulfate, so that would be a neutralization reaction. Oxidation number is going from 1 to 2, and that represents an oxidation. And manganese in the form of permanganate going to the manganese 2+ ion is oxidation number 7 going to 2, which represents a reduction. So often you're looking at one atom in a compound on either side of an equation, and you'll be asked to say, has oxidation or reduction happened? General rules for transition metals and transition metal compounds in relation to oxidizing and reducing agents are that if the transition metal has a high oxidation number, it's a good oxidizing agent. So for example, on the electrochemical series, which I'm just looking up now to find out what page it is in the data booklet for you, apologies, which is on page 12 in the higher data booklet. You can see near the bottom, which we know are the good oxidizing agents, or oxidation agents, or oxidizing agents, we can see that dichromate and permanganate are near the bottom. The reason they're near the bottom is because they have high oxidation number and they are easily reduced because they are so oxidized. So they will easily be reduced and as a consequence oxidize other things. Now you can probably imagine that if having a high oxidation number makes you a good oxidizing agent, having a low oxidation number will make you a good reducing agent. And so if you look, all of the good reducing agents, which are the things in the top right-hand side of the electrochemical series, are things like lithium, cesium, rubidium. All of them have an oxidation state of 0 because they're elements. And they are easily oxidized and as a consequence will reduce other things. So the rule is high oxidation number makes you a good oxidizing agent, low oxidation makes you a good reducing agent. There's not a real exact science, there's no such thing as if you have an oxidation number above this, you are an oxidizing agent. If it's below this, you are a reducing agent. I wish there was a rule, it would make things easier. However, in general, high oxidation numbers, anything 4 and above, chances are you are an oxidizing agent, but it's not definite. And for metals, if a metal is a pure metal, it's not going to be an oxidizing agent. The only thing it can be is a reducing agent. However, if it's got an oxidation number of 1 or 2 or 3, it could be either, really. So that was our introduction to transition metals, and we looked at how to fill the d orbitals, looking specifically at the exceptions to the rules that we see in chromium and copper. Then we looked at how we can work out the oxidation number and state of transition metals within compounds, and then we were able to relate that to the ability of a transition metal to oxidize or reduce other things. So this was our first video on transition metals. As I said, there will be 2 more, and look forward to seeing you then.